You are seeing what we're going to talk about today. It's going to be ag sizing. How is it different and what must we watch for? So some important things. Remember, you can always go to www.pentairlearningcenter.com and sign up for our what we call the PLC. And when you sign up for that, that gives you the opportunity to go in and review some of our pre-recorded webinars. So you certainly can go back there and look at anything that you'd like. All right. Now this webinar is going to be a little longer, I think, than some of them, just because of the size or magnitude of what we're trying to accomplish here. So we're going to get started on it right away here. And the first thing we're going to do here is we're going to notice that um, we've got a system here. We're going to do an example. This is called example A. And example A says we have a system that has a maximum elevation change of plus 20 feet. The maximum operating pressure required is 50 psi. There's 5,000 feet of 6-inch OD steel pipe with one 6-inch 90 and one 6-inch 45. Now, what we're trying to accomplish in this is we're trying to determine what the system requirements are. All right. So with that thought in mind, the elevation head, you might notice there, was plus 20 feet. So we have to add that in because that's something that our pump has to overcome. It has to produce 50 psi at the end of the pipe. So in feet, if we take 2.31 times 50 psi, we're going to get 115.5, which will round off to 116 feet of head there. That's required by our system. All right. The actual length of pipe is 5,000 feet. Now, if we look in our book here, you're going to notice the two things we're looking for. I'll go back there for a second. The two things we're looking for is that 6-inch 90 and the 6-inch 45. Now, basically what happens when you have a 90 like that, a piece of pipe, you'll notice here it says friction loss through pipe fittings in terms of equivalent length of standard pipe. So in other words, what we're doing is we're going to turn it into a straight piece of pipe. By the way, this page comes out of the B9020, which is the Berkeley Engineering Manual. And again, what you're doing is you're taking an elbow like this, and you're converting it to a straight piece of pipe. You're saying that this elbow is going to equal this many feet of straight pipe. All right? So when we look here, you'll see the actual size of the pipe is there, and then it goes into the standard elbow, and over there is your 45-degree elbow. So if we go down to 6-inch pipe and we look at that standard elbow, it says 16 feet. So one standard 6-inch elbow equals 16 feet of straight pipe. It'd be the same as if I was pushing that water through 16 feet of straight pipe. A 45 is going to equal 7.7. You know what we're going to do. We're going to round that 7.7 off to 8. All right? So the total effective length of pipe. Now remember, this is the length of pipe that we are going to go to the friction loss chart with. The total effective length of pipe is going to be the 5,000 plus 16 plus 8, which equals 5,024. All right. Now, if you look on page 4 in the B9020, you're going to find this right here. I'm going to break it down so you can see a little bigger. We're going to pull that one chart out. We'll put it right here. You'll notice there are 4 columns in each one of these pipe sizes. Okay. The first column is going to say gallons per minute. Okay. Second column is going to say velocity in feet per second. The third column is going to say velocity head. This is a formula that Bernoulli came up with to help us to understand that we're turning the speed of the water into energy. Okay. And then the last column gives us the head loss per 100 feet of pipe. We use the Williams and Hazing formulas. Okay. So if we look here at 200 gallons a minute, our friction loss is 0.7 feet per 100 feet of pipe. At 300 gallons a minute, we're at 1.6. 400 puts us at 2.7. 500 at 4.1, and 600 at 5.7. So we're going to take those numbers, and you can see we're going to put them in over here in the column that says friction loss per 100. So in our chart, we've got gallons per minute, that 20-foot elevation. We're always going to need that 50 psi, so all the systems require that. Then there's your friction loss per 100. Your total friction loss, remember, you're going to take that 5,024 feet, you're going to divide it by 100, which gives you 50.24 100-foot lengths of pipe. And then you multiply that times your friction loss per 100 to get your friction loss. And then that's going to give us our total system head demand. All right? So we're going to start out simple. We're going to say, geez, we're not going to use any water at all. We still need that 20 feet of elevation. We still need that 116 feet for the pressure. Obviously, because there's no water moving, there's no friction loss. So our system head demand is 136. All right? Now, if we go down to the 200-foot line, you'll notice we still need those two things. Our friction loss went up to 0.7, so our total friction loss in our 50.24 100-foot lengths of pipe is 35 feet. If you add the 35 to the 136, you come up with 171. All right? So what's the system head demand for 300 gallons? Anybody want to take a stab at that? It's real simple. All you have to do is take the total friction loss and add it to 136, and that gives you your total head. In this case, it's 216. At 400 gallons a minute, we're going to be at 272. At 500 gallons a minute, we're going to be at 342. And at 600 gallons a minute, we're going to be at 422. So you can see that all we're doing is taking the total friction loss and adding it to that head that's going to be there no matter what. The head that's going to be there no matter what is our elevation and our system pressure requirement. All right? So system head demand affects the pump performance. Yes or no? The answer is yes, it does. Oh, there we go. We got a right answer there. Yes, it does. It does affect it. It is one of the questions that's on our 20 questions quiz. When you come to the factory school, we ask you that same question. System head demand does affect pump performance. The answer is absolutely yes. How does it do that? Well, notice here in our chart, right there, we're at 0 gallons a minute, 136 feet ahead. The next one we said was 200 gallons a minute at 171, then 300 at 216. We went all the way over to 600 at 422. If we take our pump curve, this is our system curve. If we take our pump curve and cross it, you can see that we're actually going to be running right around 390 gallons a minute at about 260 feet of head. So this pump is going to perform right there on this system head curve. All right? So the conditions here are 6,000 or 5,000 feet rather of 6-inch OD steel pipe with 190 and 145. That's what we're looking at, okay? Now in example B, we're basically going to do the exact same thing with one exception. You'll notice we went to 8-inch OD pipe. So our elevation head is going to remain the same. Our pressure requirement is still going to be 116 in feet, remember. The actual length of pipe didn't change, it's still 5,000. However, because we're using 8-inch, an 8-inch elbow, and an 8-inch 45, if we go here and look at these, we see that that 8-inch elbow is going to be 21 feet, and that 8-inch 45 is going to be 10 feet. So now if we add all our equivalent length of pipe together, we wind up with a total of 5,031. So we went up a little bit from 5,024 to 5,031 in total length of pipe, but let's see how that 8-inch pipe is going to affect our system. So you'll notice here, this is the 8-inch OD pipe out of the B9020, okay? At 400 gallons a minute, we're at 0.69, which is just about what we were with 200 gallons a minute in the 6-inch pipe. 500 gallons a minute is 1.05. 1,300 gallons a minute is 6.12. And if you look, you can see those numbers are pretty similar to what we saw before, only we're doubling our flow. So of course, what we see here is that at zero flow, the system is the same. Whether it's 8-inch pipe or 6-inch pipe has no effect on that system if there's no water flowing through it. The requirements are still 20 feet of elevation and 116 feet for that 50 psi. Okay, as we start flowing water through there, now you can see we go to 171 all the way up to 443. So because we went up in pipe size, that allowed us to do a little bit more. So if we look at our system here, now we see zero flow, still the same at 136, and 1,300 gallons a minute is now up there at 443. Okay, if you put the two together, this is what they look like. The one on the left, the system curve on the left is a 6-inch pipe. The system curve on the right is the 8-inch pipe. And you can see that by changing our pipe size, that's going to change the amount of water and head that the pump will be able to do. All right? Now, let's take a little example here. We've got a rancher. He's recently reclaimed a quarter section of land by clearing off the brush growth and now intends to plant and grow a marketable crop. He has been limited to less than 1,000 gallons per minute of water by the state agency that has control over the water. Okay? An irrigation specialist has estimated his required water application rate based on the soil conditions and the proposed crop to be 815 gallons per minute. He has suggested that the sprinkler irrigation will give him the most efficient use of his limited amount of water. The bid he receives is for a center pivot irrigation system that will require 820 gallons a minute be delivered to the base of the system with a pressure of 70 psi. All right? For simplicity, we will define that the system pressure required will remain constant in the flow range. Now, if we take a picture here, this is what we're talking about right here. There's our center pivot, and of course, if we get the what they're saying to us is if we get the 70 psi at the center pivot, they've already calculated all the losses through the rest of the system. So they just say we need 70 psi there. All right, makes it much simpler for us. All right, now let's take a look here. The water source is a surface pond with a spillway that controls the maximum height. The pump will be installed 2 feet above the full level of the pond. A liquid level control will shut off the pump when the water level of the pond drops 5 feet. Now that means then that our maximum vertical lift on the suction side will be 7 feet. The base of the pivot is 27 feet above the pump and 1,350 feet away horizontally. 460 volt 3-phase power is available. However, he needs to determine if it is more cost effective to power the pump with a diesel engine. So we're looking at the difference between a closed couple motor drive pump or an SAE engine drive. And that's what we're going to look at. We're going to look at both of those. All right. So again, here's our picture. If we read what our paragraphs told us, we've got 7 feet maximum of lift, vertical lift on the suction side, and we've got 27 feet of discharge elevation. Now remember, on the suction side, we're always going to call it lift. On the discharge side, we're always going to call it elevation. Okay? So now let's read a little bit about our suction side. The main run of the suction pipe will be 10-inch ID steel pipe. On the end of the pipe, there will be a 10-inch basket strainer submerged 5 feet below the low-level cutoff. A 15-foot length of 10-inch ID steel pipe will slope upward to the pump center line, which is we call the datum plane, where the 10-inch 90-degree standard elbow will direct the flow into a 4-foot length of horizontal pipe 10 inches in diameter. Okay? A 5x10 eccentric reducer, and I'm going to show you what that looks like so you totally understand it, will connect the assembly to a 3-foot length of 5-inch ID steel pipe for the final transition into the suction intake of the pump. So we're using a 5x10 eccentric. All right? Now, if we look at the picture again, let's put it all together. There's our 10-inch basket strainer down there. There's 15 feet of 10-inch pipe because we're at an angle. 15 feet of 10-inch pipe there. There's 190, and there's a 4-foot section of 10-inch pipe. And then there's a 5 by 10 eccentric reducer. All this gets counted into one side, okay? Our other thing that we need to concern ourselves with on the suction side is the 5-inch steel pipe, which is 3 feet long. All right, so let's take a look here now. On the discharge side, we're going to start out using 6-inch Schedule 40 PVC to emphasize the impact of pipe sizing on the system efficiency. The pipe run from the pump will be straight and will have 1,350 linear feet of underground pipe with 245s and 290s. All right. There will be a 6x4 eccentric reducer installed on the piping system just past the discharge valves. The discharge valves, there's a 4-inch check valve installed in the pump and a 4-inch butterfly valve installed after the check valve to regulate the flow when filling the system. And there will also be 2 nipples, one used between the check valve and the pump, one used between the butterfly and the check valve. Okay. The two together will amount to about 2 feet of pipe. Now, if we look at our discharge side, once again, you know, I kind of colorize things so you understand pipe sizes. I want to make sure you understand that, okay? So we've got our 6-inch Schedule 40 PVC, 1,350 linear feet with 245s and 290s. Also is our eccentric reducer. That's going to count on that 6-inch side. Then we've got our 1 by 4-inch nipple, 1 foot by 4-inch. Then we've got our 4-inch butterfly, another nipple, and our check valve. Okay, so those are the things in the discharge side of the pump. Now, when we look here, remember section A, that's the first big size suction pipe, is 10-inch. Okay, we're going to measure it from there to there. That's all 10-inch pipe there. Okay, section B is 5-inch pipe. It's going to go from that point to this point. Section C is a smaller discharge pipe. It's going to go from the eccentric to the pump, all right? And then section D is our 6-inch larger pipe. It's going to go from that eccentric to our center pivot. So everybody understands the 4 different pipe sizes that we're using here and what they're going to mean. We're going to call them section A, section B, section C, and section D. So we'll start out with section A, which is our large diameter suction pipe. Remember, our flow rate was 820. Our lift is always mentioned in Z. Z means it's vertical feet. When we're on the suction side, it's going to be ZS for suction side. So lift is always going to be represented as ZS. And remember, our maximum is 7 feet. Remember that if the water is at its full level or it's only 2 feet, the pump just works better. So the 7 feet is there so that we always figure out the worst case scenario. All right. Our pipe size was 10-inch ID. The material was steel. The actual length of straight pipe is 19 feet. We've got 15 feet going from the elbow down, and we've got 4 feet going from the elbow to the eccentric. All right. Now, the equivalent length of fittings. Remember what we're going to do with these fittings. We're going to turn them into straight lengths of pipe. If you have the training manual with you, the Ag and Industrial Training Manual, we're on page 37 in that training manual. And you can see the 3 things we're looking for there. We're looking for the basket strainer, the 10-inch 90, and the 5 by 10 eccentric. So let's go to that page and take a look so you can see what we're doing here. All right. There's our basket strainer there. There's our nominal size pipe. So if we look at 10-inch pipe and that basket strainer, we see the basket strainer is worth 30 feet of straight pipe, straight 10-inch pipe. All right. If we look at that 90-degree elbow and the 10-inch pipe, it's equal to 25 feet of straight 10-inch pipe. Now, here's where we're going to understand that eccentric reducer. There are two types there. You can see the eccentric and the concentric is next to it. Eccentric means that we're flat on top. Concentric means that we have an angle. Okay, we're not flat. Now, why is that important? If I fill this pipe up with water, you can see the water is going to be right at the top and there's nothing to worry about. If I fill this pipe up with water on the suction side, you're going to notice I'm going to have a big air bubble right there that I've got to get out of there, and probably I'll wind up losing prime and have to prime this pump more than once because of that. So this is why on the suction side, you always want to use an eccentric. On the discharge, you can use either one, but on the suction side, it is imperative that we use eccentric reducers. Now, the other thing to notice is there's a formula, and the formula is the same for both of them, whether it's concentric or eccentric. And the formula says that if you take the smaller diameter and divide it by the larger diameter, of course, this is always going to give you a smaller number. That's important. So if we take diameter 1, our 5-inch diameter, by diameter 2, our 10-inch diameter, and divide the 5 by the 10, we get a 0.5. Now you're going to notice if you look underneath the eccentric reducer, it says 0.6, 0.7, or 0.8. So the question is, which is 0.5 closer to? The answer, quite obviously, is going to be 0.6. So we look at 10-inch pipe, 0.6, and we find that that particular item is worth 65 feet of straight pipe. That's the equivalent length of straight pipe. All right, so we come back here and we fill these in. The basket strainer was 30, the elbow was 25, and the eccentric reducer is 65. Now don't forget that we've got 19 feet of actual straight pipe. So if we add all of this together, we're going to wind up with 139 feet of pipe. All right, now the next thing we do to calculate head loss is we divide our total pipe by 100, and that's going to give us 1.39 100-foot lengths of pipe. The question is, what are we going to multiply that by? And so what we're going to do now is we're going to show you something called interpolation. And we're going to interpolate so we know exactly what our 820 gallons worth is worth, okay? So we look at our 10-inch ID steel pipe here. Yes, we're using ID instead of OD. Very few people use OD. The first problems were written with OD, so I had to use OD, okay? But we're going to use 10-inch ID steel pipe here. You'll notice that it doesn't say 820, it says 800 or 900. So we're going to look at both of them. And when we look, we notice that at 800, we're at 0.66. At 900, we're at 0.82 friction loss. So we're going to put the 900 on top with the 0.82. We're going to put the 800 on the bottom with the 0.66. What we're going to do now is we're going to subtract the 0.66 from the 0.82, which gives us a remainder of 0.16. Okay? The difference between 800 gallons and 900 gallons is 100 gallons. If we go up from 800 to 820, 820 is going to be 20% larger than 800. So if we take 20% times 0.16, we find 0.032. Add that 0.032 to the 800.66, and your 820 is going to equal 0.692. Now, I know this seems like a lot of math, and we say, oh, geez, do I really have to go through this? And the answer is, how important is it to you to get it right? Okay? In this case, it probably wouldn't have made too much difference because no matter what, we're going to take that 0.692, it's going to come up to 0.961, which we're going to round off to 1 foot. And even if we would have used one of the other ones, it probably would have only been 1 foot. Now, if you would have gone with a higher one, you probably would have been at 2 feet. Would it have made the difference in whether the pump worked or not? Probably not. But I want to show you so you understand how to do it properly. Okay? So the friction loss through section A of the pipe is 1 foot. Now we're going to go to section B. Remember, section B was the smaller side suction pipe, and that pipe size was 5-inch. The material was steel pipe. The length of straight pipe was 3 feet. The equivalent length for fittings, well, there weren't any fittings, so we don't have to worry about that. So the total linear feet of pipe is 3 feet, which means to calculate the head loss, we take 3, divide it by 100, gives us 0.03 times what? Well, let's go look. So we're going to go to the 5-inch ID steel pipe, and when we look here, we notice that there's 800 and 850. 800 is 18.6, 850 is 20.8. So again, we're going to line them up with the highest one on top and the lowest one on the bottom because we want to be able to subtract these rather easily. And of course, that gives us a 2.2 difference. Now, this time, if we subtract 800 from 850, we find there's only 50 gallons difference between them. So if I want to go to 820 now, that's going to be a 40% raise. So I take 40% times 2.2, I come up with 0.88, add that to my 18.6, and at 820 gallons a minute, I'm going to have 19.48 feet of head loss per 100 feet of pipe. I've only got 0.300 feet of pipe, so the total here. Anybody got an idea? Anybody have any questions? Okay, it's going to come up to 0.584, which of course we're going to round up to 1. So now what we're going to say is section B has 1 foot of friction loss. We said we're going to look at our total suction side now. And so if we look at our total suction side, section A was 1 foot, section B was 1 foot, and don't forget your vertical lift was a maximum of 7. So our total suction side head is going to equal 9 feet. All right? Don't forget to keep that in place because we're going to use that a little later. Now, the head required on the discharge side, our flow rate didn't change. We're going to put 820 in, we're going to put 820 out. Okay? Our elevation, now remember on the discharge side it's called elevation, not lift. And so Z represents feet, and we're ZD because we're on the discharge side. Okay, so there's your ZD. And your ZD is 27 feet from the datum plane of the pump to where we're entering the center pivot at is 27 feet. Okay, our PSI required is 70. If we take that 70 and multiply it by 2.31, we're going to come up with 162 feet of head. Now we need to do that because remember the pump curve is written in feet of head. So we have to know that. Now let's take a look at the smaller section pipe coming out of the pump. Remember, it's 4-inch. It also happens to be PVC. All right. The actual length of straight pipe is 2 feet, and that's for those 2 nipples that are in there. Okay. The equivalent length of fittings. Well, what are the fittings we have? We've got a 4-inch check valve and we've got a 4-inch butterfly valve. So if we look on page 37 again, and yes, a few people have said to me, well, this is steel fittings. What about plastic fittings? And I'm going to tell you right now, plastic fittings actually tend to be a little bit more than steel. So, but all I've got is steel here, so that's what we're going to use. All right. And so we look at our nominal size pipe, which is 4-inch. We look at the check valve there, and the check valve is 17. We look at the butterfly valve, and the butterfly valve is 7. So now we go ahead and we've pumped those numbers in. Don't forget you've got linear feet of pipe on the front side there. That first page, we had 2 feet, so 17 plus 7 plus 2 is going to equal 26. So our head loss now, to calculate it, we take 100 divided into 26, we get 0.26 times what? Well, let's calculate that out. All right. At 850 gallons a minute, we're at 30.1 feet of head loss per 100 feet of pipe. At 800 gallons a minute, we're at 26.8. If I subtract 26.8 from 30.1, that's going to equal 3.3. Now, just like before, the difference is 50, so we want 40% of that 3.3. So I take 0.4 times 3.3, and I wind up with 1.32 feet of head loss. Okay, I'm going to add the 1.32 to the 26.8 because we're going up, remember, and that's going to give my 820 28.12 feet of friction loss per 100 feet of pipe. So if I take my 0.26 times 28.12, okay, this one's going to surprise you. All right, if you got your calculator, you already did it. If you don't have your calculator, this equals 7.31, which of course we're going to round off to 8 feet. So that's 8 feet of head loss just in that small section of pipe coming from the pump, the discharge of the pump, to the 4x6 eccentric reducer. So section C has a friction loss of 8 feet. Next thing we're going to do now is we're going to look at section D. Remember, section D is going to be our 6-inch pipe. The material is still Schedule 40 PVC. The straight length of pipe is 1,350 feet. Don't forget, we've got we've got a 4x6 reducer in here. The reducer or expander always goes on the larger pipe size, so that's why you have to put it here. We've got 2 elbows and we've got 2 45s. So again, if we look in our book, our nominal pipe size is 6-inch. Our 45 is equal to 8 feet. Our 90 is equal to 15 feet. And our 4x6 eccentric reducer, if we take 4 by 6, that's going to equal 0.66. 0.66 is closer to 0.7. So 0.7 is 6-inch pipe is 9 feet. Everybody see how we calculate that? So we fill those numbers in. 9 for the reducer, 30 because we've got 2 elbows, 16 because we've got 2 45s. If we add that total length of pipe together, don't forget we got 1350 from the other page, we're going to wind up with 1405, 1,405 feet of pipe. If I take that 1405 and I divide it by 100, I come up with 14.05 100-foot lengths of pipe. Now again, it's times what? Well, again, we're going to look at our friction loss. At 850, it's 4.21. At 800, it's 3.74. The difference is going to be 0.47. Remember, we're 50 gallons. That makes it 40%. 40% of 0.47 is going to be 0.188. Add that 0.188 to the 3.74, and our 820 gallons is going to equal 3.928. So we come over here and we take 3.928 times 1405, and what do we come up with now? 55.188. We'll, of course, round it up to 56. Okay, so now our head loss through section D is 56 feet. All right, so our total suction side we said was 9 feet. What about our total discharge side? Well, remember, we've got 27 feet for our elevation, for elevation. We've got 162 feet for the 70 psi. We've got 8 feet of friction loss in the C section of pipe and 56 feet of friction loss in the D section of pipe. If you add that all together, that comes up to 253 feet of pipe. So the suction side is 9, the discharge side is 253, the total dynamic head is 262, 9 plus 253. Remember, we want a flow rate of 820, so what pump are we going to select? Well, we need to make this simple because we're online, so we're going to actually show you a curve. The curve is for the B4 EPBM. All right. Now, if you look at this curve, you're going to notice we want 820 gallons a minute at 262 feet of head. And you can see that falls between the 75 and the 60. Okay. Now, there is a formula to help us to know what horsepower we need. And so if you look carefully, we're almost on that 82%. So what we're going to do is we're going to fill our formula out. The formula says take the flow rate times the 262 feet of head divide that by 3960, a constant, and then divide that by the efficiency, which we said is about 82%, and we come up with 66.16 horsepower required. Now, there's also going to be an impeller trim, and so we would pick the impeller trim there too. Now, the other thing we're going to notice here is if we go to the diesel engine. So that was the closed couple motor drive. Now we're looking at our SAE diesel mounted pump. Okay, and once again it's 820 by 262. And you can see if we do a little interpolating there, we're about 75% efficient or 77% efficient. All right, so we run our formula here, 820 times 262 divided by 3960 divided by 0.77 equals 70.45 horsepower. All right, so what pump we picking? Well, it depends. If we want the electric motor pump, we're going to have to use a 75 horsepower with an 8.5 inch trim. Or we can use the B4JQBH. Remember, it is a variable speed pump anyway, so that's going to only require 71 horsepower. All right? Now, I want you to understand something. We picked 6-inch pipe for a reason so that you could see what happens if you go with 6-inch pipe. Sometimes, especially when you're dealing with farmers, they've got this in their head, I already own this size pipe, I'm not buying new pipe. Okay, so let's show them what would happen if they did buy the new pipe. All right, so now our pipe size is going to be 8-inch. It's still going to be Schedule 40 PVC. The length of pipe didn't change. It's still 1,350 feet. Remember, though, that our fittings are now 8 by 4, which is going to equal 48 feet. It's now two 8-inch 90s, which are going to be 40 feet, and it's also two 8-inch 45s, which are going to be 22 feet. So if we add all that up, the total linear feet of pipe went up to 1460 from 1405. Okay, but we did go up to 8-inch pipe. So if we take that head loss to calculate our head loss, we're going to take the 14.6 and multiply it by. So let's take a look. At flow rate of 850, we're at 103. At a flow rate of 800, we're at 0.89. If we subtract the 0.89 from the 103, we come up with 0.14. Once again, we're 50 gallons difference, so our 20 gallons is going to make up 40% of that. So I take 0.4 times 0.14, I come up with 0.056, add that to the 0.89, and at 820 gallons a minute, I'm going to be at 0.946. Okay? So if I take my 0.946 and I multiply that by 14.6, I come up with 13.81. Of course, we're going to round that up to 14 feet. So the head loss through section D here is now 14 feet. So let's take a look at what that's going to do. Our suction side was 9 feet. That didn't change. On our discharge side, we still have that 27 feet of elevation we have to take into consideration. We still have that 162 feet of head for the PSI that we're required to have, which is 70. Section C didn't change. It was still 4-inch pipe, so it's still going to be 8 feet of friction loss there, but we bring our section D pipe down to 14 feet. So now if we add all that together, it comes up to 211 feet. All right? So now our total dynamic head is 220. 9 plus 211. We still want 820 gallons a minute. That didn't change. So which pump did we select? Well, let's take a look. If we look at that same pump, the B4EPBM, all right, we want now 820 gallons a minute, but only at 220 feet of head, and you can see we're a little bit under the 60 horsepower. Okay, our percentage-wise, we're at about 80.5% for efficiency, and again, we're kind of guessing at that. All right, so we take our 820 gallons a minute times the 220 feet of head we want, divide that by 3960, our constant, and then divide that by our 0.085 for our efficiency, and we come up with almost 57 horsepower, 56.59. All right? Now again, the P there indicates that we are talking about our electric motor pump. Let's change the pump. Let's go to our cube pump now, which is our SAE engine mounted pump. All right? There's our 820 gallons a minute there, and there's our 220 feet of head on this one. And now you're going to notice we're right at about 78%, and again, we're kind of guessing there. Okay? So we take 820 times the 220 feet of head, divide it by the 3960 constant, divide it by the 0.78% of efficiency, and that's going to equal 58.4 horsepower. Okay? So in this case, we have a choice of a B4 EPBM. We're only going to use 57 horsepower. Now, of course, we have to buy a 60 because that's all they sell it in, but we're only going to use about 57 horsepower here. And, of course, we're going to trim the impeller again to 8 inches. Or we could use that B4JQBH, and we'll only be using 59 horsepower. Now, let's do a little comparison here. If we use the 6-inch pipe, now remember the purpose of this comparison is to try and convince our farmer to buy the 8-inch pipe. So if we use the 6-inch pipe that he's got, it's going to require 75 horsepower motor on our electric motor pump, and we're still going to have to trim the impeller. That impeller trim, by the way, is about $263. Or we could use the B4JQBH. Now, what we need to do at this point to help him to understand what's going on is we need to know what is the cost of electricity. And I will tell you a formula. It's not 100% accurate, but at least it gets you in the ball field here. When it comes to diesel fuel says that 10 horsepower per gallon per hour. So for every 10 horsepower I'm running, I'm going to use about a gallon of fuel for every 10 horsepower per hour of running. Okay? So in this case, with the 71 horsepower, we're talking about a little over 7 gallons of diesel fuel that we're going to use. If we go to the 8-inch pipe, because our TDH now dropped to 220, we can use a 60 horse B4 EPBM, so we're saving money on paying for that pump. Plus, again, if you calculate your cost for electricity, you'll find that it's going to be quite a bit less than if you use the 6-inch pipe. Or again, you can use the B4JQBH, which now you're only going to use about 6 gallons of diesel fuel an hour. So you're saving a little over a gallon of diesel fuel per hour. Very important that we understand that. Okay? Now, I did mention yesterday when we talked about BEC 2 that if you wanted to, you just needed to plug in numbers to BEC 2. All right? So, when I plugged in the numbers and I came up with 820 gallons a minute at 262 feet of head, and I said I want to pick electric motor drive pumps and I want to pick SAE engine mount pumps. Okay? You'll notice that it picked an SAE engine mount pump first, the B4EQM. I do want to point out that while they picked that because it was the best efficiency, but while it was the best efficiency, if you look at the NPSHR, it's over 18 feet. Now remember, we had a maximum of 7 foot of lift. If you add 7 and 18 together, you're over 25. That makes that pump very questionable for our job. Okay? And this is why we need to take a look at that NPSHR, because sometimes the most efficient pump isn't always the best pump. The next most efficient pump happens to be the B4EPM, or B4 EPBM rather, that we chose, and you'll notice it has an NPSHR of not quite 14. So if you add 7 to 14, that's 21. You could probably be up close to Denver and still make this pump work. Okay. Then it picked a 3-inch pump, but again, look at the NPSHR on that. Then it picked our B4JQBH, which we picked, which has an 8.25, really good NPSHR there. Okay, if I was in altitude, that's probably the pump I would want to pick. My efficiency did drop about 5.5%, but when you take into consideration altitude, um, that NPSHR kind of wins out. Okay, so that's if I'm going to use 820 with this is with the 6-inch pipe. All right, and again, if you look at the horsepower rating, now this is the horsepower required to do the job we want it to do. It's 66.15 for the electric motor drive and a 69.78 for the SAE. And I think we calculated it a little bit differently. We came up with 71, I think it was. Okay. If we look at the 8-inch pipe, so we go to the 8-inch pipe where now we need 820 at 220. Okay. It picks the exact same pumps, but you'll notice the NPSHR and that B4EQM went up, which really does make it impossible to use that one now. The first one that we picked, the B4PBM, you'll notice the efficiency there. The NPSHR pretty much stayed the same, and the power rating went down a little bit. Well, quite a bit to be honest. It's 56.45. It was almost 70 before. And the B4JQBH, again, our NPSHR went down because we're using bigger pipe, and the pump efficiency, it changed a little bit. It went down too. But look at that horsepower requirement. It dropped by pretty close to 14 horsepower. So really, you can see the advantages to using the Beck program, but of course, we just showed you how you can do it without Beck. The point is you have to know where to look. Beck helps you to steer you in the right direction. That's one of the reasons why I use Beck, is because it steers me to what I want. I generally will go back once I've calculated it on Beck, and I'll take a look because sometimes it doesn't always give me all the information I'm looking for. And so I take a closer look at the curve, but at least I know which curve to start looking at. All right? Anybody have any questions? Interpolating is not the easiest thing in the world, and I know that it's not. But if you interpolate, it gets you right to where you want to be. And that's why I showed you interpolating. By showing you interpolating, I actually got Beck to pick pretty close to the same exact thing we did, and we did that by interpolating. Take care, and thanks now. Bye.